particle of mass 5 kilograms is suspended from a fixed point by a light elastic string which hangs vertically. The elastic constant of the string is 500 newtons per meter. The mass is pulled down a vertical distance of 20 centimeters from the equilibrium position and is then released from rest. So let's look at the situation of the string before a mass is attached. So the string is hanging with its natural length. A mass of 5 kilograms is attached to the string. So the string gets stretched by a certain amount. Let's say that that amount is d. Now, the mass is hanging here in its equilibrium position. So it's hanging here at rest. So the resultant force on it is 0. The forces acting on it are its weight, which is mg, and there must be an equal and opposite force acting up, since the particle is at rest here. But by Hooke's law, we know that this force is due to the string, and the string force, or spring force, well, it's a string here, is proportional to the extension of the string, which is d, and the proportionality constant is the spring constant, which is 500. So the magnitude of the string force is the spring constant times the extension, 500 times d. Now the mass is set in motion by pulling it down a distance of 20 centimeters, which is 0.2 meters, and then releasing the mass. We know what will happen because I covered all of this for the general case of a mass m. But here we're just using specific values, but it's the exact same as what I did before. We know that this mass will oscillate about x equals 0 indefinitely if there is no friction force. We're assuming no friction force. So that means that the amplitude of the motion will be 0.2. So the maximum displacement of the mass from the equilibrium position is the amplitude. Now, we want to, in the first question, show that the particle moves with simple harmonic motion. As I've said, we've done all that before for the general case of any mass m. But let's just do it again here for these numbers. Okay, so the mass is oscillating about its equilibrium position. Let's suppose that the mass is at some position x. X could be positive or negative. Well, actually, if we take upwards as positive, then downwards will be negative, but it doesn't matter which sign we assign to any particular direction. Anyway, let's look at the mass, say, when it's at some distance x from its equilibrium position. It could be below the equilibrium position, as it is here, or it could be above the equilibrium position. Let's look at the forces acting on this mass. Well, we still have its weight, which is 5g. We have the string force, which is the string constant, or elastic constant, we should say here when we're talking about a string, of 500 newtons per meter, multiplied by the distance of this point here down to this point here. So we're looking at the extension of the string. So the string was initially this position, so the extension is this distance here. It's quite easy to work out the extension when the mass is below the equilibrium position. The extension is d plus x. Although I'm making x negative here, so I should really say d minus x, just to be careful. Signs can be very tricky. D minus x. Say for example d was 0.1 meters, and suppose x would be negative, x is minus 0.2, then d would be, or sorry, the extension would be 0.1 minus 0.2, so the extension would be 0.3. When I covered this more general situation in an earlier video, the video entitled Mass on a Vertical Spring, I looked at the absolute value of this quantity. It's by putting vertical lines on either side. But I'm going to leave them off for now. I won't go into those details now. Um, we'll just assume that the mass is below the equilibrium position. Everything actually works out if the mass is above it. It's just a little bit, you have to be careful about getting the distance of the new position of this point from the equilibrium position. When the mass is above the equilibrium position, there's a few little small points you have to watch for. But we just take this case here for now. We'll say that F string is 500d minus x. Then the resultant force is going to be this force here, which is positive, because d minus x will turn out to be positive for this situation. 500 times d minus x, that's 500d minus 500x. So that's F string minus this force here, Fg, because this is in the negative direction. But we already saw that 5g equals 500d, so these cancel out. So we see that the force is a negative scalar times the position x. That means we have the equation of motion for a particle undergoing simple harmonic motion. The force is a negative scalar times x. Now if you like, you could write this in terms of acceleration, since the resultant force on an object is mass times acceleration. The acceleration of the object, I'll call it a, or x double dot. You could say that the acceleration is a negative constant, in this case minus 100 times x. So you could use either of these. These are identical. We saw before, well, we proved before, that x equals a sine omega t plus phi is a solution for the equation of motion of a mass undergoing simple harmonic motion. Omega is the square root of k over m. A is the amplitude. So for our example, the amplitude was the initial displacement of the mass. The mass is pulled down a distance of 0.2 meters and released, so its amplitude is 0.2. So it'll oscillate with that amplitude indefinitely if there's no friction. Omega is root k over m. We can calculate that because k is 500 and m is 5. 500 divided by 5 is 100. The square root of 100 is 10. Now we want the initial position of the mass to be either plus 0.2 or minus 0.2. Actually, it's minus 0.2 here because I took downwards to be negative. But it turns out that we could have x naught equal to plus 0.2 as well. Turns out it doesn't matter whether the mass was released after being pushed up a distance of 0.2 meters from the equilibrium position, or after being pulled down a distance of 0.2 meters from the equilibrium position. Turns out it doesn't matter. If we set phi equal to pi over 2, then sine of any angle plus pi over 2 is the same as the cos of that angle actually. See, we can set phi equal to anything we like. We could even replace this with a cos function. Why would we want to do that? Why do we want cos here? Well, it's because the cos of naught is 1. So we'd have 0. So at t equals naught, we'd have 0.2 times 1, which is 0.2. That's what we want actually. Ideally, we want minus 0.2. Actually, one way we could do that is just make a negative. So yeah, we could mirror this situation exactly. So now you see that x at time naught is minus 0.2 times cos of naught, which is minus 0.2. That's what we want. But plus 0.2 would work just as well. Normally, actually, a is meant to be positive, but it doesn't matter. This will work as well. We want to find the speed and the acceleration of the mass 0.1 second after it is released from rest. Well, to get the speed, we just differentiate x with respect to time. Get the x dt, or sometimes it's called x dot. That's the speed, or the velocity actually. More accurately, it's the velocity. Now, differentiating this with respect to time, the derivative of the cos function is minus sine, and we multiply by the derivative of the angle, which is 10. So we have 10 times minus 0.2, that's minus 2. So this is the velocity at any time. So if we want the velocity at t equals 0.1, we just plug 0.1 in here, so we have minus 2 times sine of 10 times 0.1, which is sine of 1. So that 1 is 1 radian. Actually, this is a plus sign here, but it doesn't really matter. So the velocity comes out to be plus 1.68. We're getting the magnitude of this quantity anyway. So the speed is 1.68 meters per second. The velocity comes out to be positive as expected, because when the mass is released, the velocity vector is pointing upwards, the positive direction. But we're only interested in the magnitude. So even if this came out to be negative, we'd have to make it positive. So the speed could be shown like this. The speed at 0.1 seconds. We just put vertical lines on either side. To get the acceleration, we differentiate the velocity with respect to time. The derivative of the sine function is cos, and we multiply by 10. So 10 times 2 is 20. So that means that the acceleration at 0.1 seconds is 20 times the cos of 10 times 0.1, which is 1. So it's 20 cos 1. So we get the cos of 1 radian, and multiply by 20. So we get 10.81. meters per second squared. So this is the acceleration vector. It's positive. But we're just interested in the magnitude, so we can leave our answer like this. The magnitude is also positive. By the way, there is one point about this situation that differs from a mass on a spring. Basically, we do not have a spring, we have a string. So when the mass passes through its equilibrium position, it's moving up the way, the string cannot be compressed. So simple harmonic motion really only occurs for when the mass is moving towards the equilibrium position just after it's released. So we can't apply the formulas for the situation of the mass above the equilibrium position. It will carry on a course a certain distance above the equilibrium position. It has a certain amount of inertia, it was moving, but the string does not get compressed, so the equations aren't valid. So all these answers here are valid, provided that the mass was below the equilibrium position, or is below the equilibrium position when t equals 0.1. Just as an exercise, we will calculate x at t equals 0.1 just to see where it is. Hopefully it's below the equilibrium position. So x at 0.1 is minus 0.2 times the cos of 10 times 0.1, which is 1. See, this will come out to be negative. Get the cos of 1 radian and multiply it by 0.2. Well, it's minus 0.2, so we get minus 0.1 approximately. So the position is negative. This sign is important. It's negative, which means that at t equals 0.1, the mass is below the equilibrium position. So everything we have done is valid. For later times where the mass passes through its equilibrium position, then we don't have simple harmonic motion. The string becomes slack.